Hey, let's start in for the day. And this is part, I guess, 2 of a series of lectures that are really about learning representations. So, you know, we talked about artificial neural networks last time, but one of the most fascinating things to me about artificial neural networks is that they are a way of learning a new representation of the input data. And so we're going to continue on that theme today and also on Thursday and look at a variety of other methods. The well-known XCA methods, like PCA, ICA, and CCA, we're going to talk about today. Just kind of take a survey of different methods in machine learning for learning representations. So let's get on with that. This is a slide we talked about last time, but I put it up here just to remind us what I mean by learning a representation. Here we have a neural network that's trained by giving it training examples where the input is a photograph and the output is a classification of the face in that photograph according to whether the person's looking left, right, up or down. And as we saw, when the network is trained, it can do this task with quite high accuracy, 90% plus accuracy. And interestingly, if you think about it, this input image, which is 30 by 32, so it has 900 features, once this network is trained, it has found, whoops, can't do that. It has found a way to re-represent that 30 times 32, 900 pixel input in terms of just 3 numbers. And that doesn't preserve all of the information about the photograph, but if you think about the objective function that we're using to train the neural network, which is to minimize the sum of the squared errors in its output, predicted output values, then what the neural network will do essentially is try to find the best 3-number representation, 3-dimensional representation of this 900 plus dimensional input image. And when I say the best 3-dimensional representation, I mean the one that will minimize the sum of squared errors in predicting whether this face is looking which of those 4 directions. So in this sense, the neural network has a side effect of trying to fit the input-output signal in the training data, ends up learning a re-representation, in this case a much lower dimensional, 3-dimensional representation of that input. So before we leave neural networks, I wanted to talk about one more example that illustrates another direction of work in neural networks, which has to do with their use in modeling cognitive processing in humans. And this is a neural network taken from a paper in Nature a few years ago by Jay McClelland. And what this network does is, you can see the input is, there are 2 sets of inputs here. This one, which codes in a 1 out of n fashion, in input like pine, oak, rose, daisy, robin, canary, etc. And also an input that encodes the name of some relation, like is a, or has, or can. And the network is trained to fit assertions like this one, which asserts that canaries can fly. And the way that's encoded is shown here. The dark green means that these are activated units. So the dark green ones would be a 1. The others would be a 0. So if we want to represent the training example that canaries can fly, the way we do it with this network is we make canary here a 1, and we make can, the relation can, a 1, and then we on the output side, say, well, canaries, they can fly, so we'll make fly a 1. Canaries can also do other things like sing and move and grow, so we make those 1s too. So one thing I like about this example is it kind of stretches your thinking a little bit about what we can do with these propositional representations that neural networks use. So, and in fact, you can see this has a couple layers of neural network, hidden layers, I'm sorry, in the neural network. And it's a completely connected feed-forward network. And therefore, we can train it using the backpropagation algorithm that we talked about last time. And indeed, that's what McClellan did in this case. And so I like this network because it kind of makes you think about different ways of representing things. Yeah?
Is there any reason why they structured it this way?
Yes, there is a reason they structured it this way, which we're about to see. They were interested in the question of how do hierarchies emerge, hierarchies of categories emerge, and so they structured it this way to make it easier to study that question. So let's see what I mean by that. And so this is kind of a summary of this paper that was in Nature. What they point out was that there's this properties of humans that sometimes humans develop deficiencies of cognitive deficiencies of different types. One is called semantic dementia. And people who have semantic dementia lose over months or years of time knowledge about objects. In particular, they lose the more specific details in the hierarchy first. And so, for example, before they have semantic dementia, if you show them a picture of a canary, like you and I, they'll have no trouble saying, oh, that's a canary. But as the disease progresses, then they get to the stage where they can identify it as a bird, but they can't say that it's a canary. And much later in the disease, maybe they could just say it's some kind of animal. So the disease progresses by taking away, in a sense, the more specific layers in the hierarchy first. So they bring this up as an example of evidence that humans act as though they have some kind of hierarchical organization of concepts. And they also point out that children, when they learn to speak, for example, first learn a word like bird, and then sometime later they learn distinctions like canaries versus robins versus roosters, etc. So there are a couple, I mean, a lot of evidence that people act as though they have some kind of hierarchical organization of concepts and memory. And so they're interested in the question of what learning mechanism could produce this kind of emergent hierarchy from the stuff we encounter. So actually, here's one bit of evidence they give. A particular person who named J.L., who had semantic dementia. Here you can see at 3 different periods of time, spread out over a couple years, their ability to name objects or name the objects that are in photographs. And so in September 91, they did a perfectly good job at spotting birds and chickens, ducks and swans, but had difficulty with these other objects. Later on, you can see they could identify these things were birds, but had lost the detailed ability. And then much later, even had some difficulty with those. So there's a typical kind of progression. And so what they did was again, the question they were focused on is what kind of learning mechanism might explain the emergence of these hierarchies? And their conjecture was that artificial neural networks could model this kind of emergent hierarchy appearing. And so what they did was they trained that neural network that I showed you, and they plotted. What algorithm did they use to train it? backpropagation, the same gradient descent algorithm that we talked about last time. And then what they did was they plotted during training, after, they used the term epoch, but that really means after 250, they call them epochs. I will call them iterations of gradient descent in training the network, versus after 750 iterations versus 2,500 iterations. They plotted the internal hidden unit values that were being used by the network to encode those input assertions, like canaries can fly, canary is a bird, etc. And what you find is after 250 iterations of gradient descent, you can see that these four items have very similar internal hidden unit representations. Their activations of those hidden units are about the same, whether it's pine or oak or rose or daisy, but they're quite different from these other four, which are robin, canary, sunfish, and salmon. So essentially, at that stage, you could reasonably say that it was distinguishing these living things or these animals from these plants. And then later at 750, you can see it starts to distinguish, for example, rose and daisy now have very similar representations, a little different than they used to be. But now they're quite different from the pine and the oak. And similarly, the animals have now split into robins and canaries versus sunfish and salmon. Okay, so this is what they observe when they do this gradient descent procedure, training the neural network on a fixed set of assertions and tracking what happens as a function of the number of gradient descent steps. So it's as though the network is picking up early on in the training these gross distinctions. And then as it proceeds, it shifts around the representations with more gradient descent steps to pick up more structure. So I don't want to spend too much time on this, but so let me stop there. But the reason I wanted to show you that is there is a pretty active community of researchers who try to use neural networks as what I would consider to be a pretty coarse-grained macroscopic model of the kinds of parallel computation and learning that might be happening in the brain. And here's a kind of prototypical example of that kind of work. Another person here at CMU who does a lot of this work, by the way, is Dave Plaut. Dave is a professor in our psychology department who does a lot of work using neural networks to model language processing in people. And he's very well known for this work. So it's interesting that even though probably the majority of research that has been done over the years on neural networks has been motivated by engineering goals, like we want a network that can classify images, still there's a very active sub area of work that tries to use this to model processes in the brain. Okay, and this also gives you an idea of, this is, kind of another example, another glimpse into the issue of learning representations, right? Okay, so any questions before we leave? Oh no, there's one more thing I wanted to say about neural networks. Any questions on this?
So are the reduced dimension representations that are learned telling us something, are they like akin to feature selection?
Yeah, so the question is, what are these lower dimensional representations of the input anyway? Are they like feature selection? And I think it's actually in a way, very different from feature selection, because in feature selection, if I give you, think of that first slide with the photograph as input, which had 30 times 32 input features. if we select a subset of those features, we'd be ignoring part of the image. And in fact, what those 3 hidden units do instead is they ignore none of the pixels. They just synthesize 3 new features, each one of which is some logistic function of all 900, whatever it is, 960 input features. So they're not selecting features so much as they are synthesizing 3 features, and which 3? Well, the ones that are going to minimize the final task, which is fitting the input-output data to the network. So I think of it as actually a qualitatively different thing from feature selection. Okay, so there's one other idea I wanted to run by you in terms of learning representations for using neural networks. And this ties back to last week we were talking about time series. And we're talking about hidden Markov models, for example. So one kind of interesting question is can we use this neural network idea of learning representations to learn representations that are useful for time series modeling? And remember, when we talked about hidden Markov models, we talked about the Markov assumption that HMMs make, which is that the present is conditionally independent of the distant past given the immediate past. Or time shifting 1, the next state is conditionally independent of the past given the present. But there are situations where that assumption doesn't hold. There are plenty of real-world problems where we don't really know whether this is a Markov system, or if it's an nth order Markov system that depend on n time steps back, we don't even necessarily know what n is in real world problems. So it's interesting to think about the question of learning these hidden representations using this neural network kind of approach. And so, for example, imagine a robot. A simple example of this could be a robot that's just got a camera. And it's only got a limited field of view. It can't see, it doesn't have eyes in the back of its head, just like you. So if it's trying to predict the result of the next state, and let's say it can take actions like going forward or turning, then obviously if it turns and sees, oh, there's a computer there, if it turns here, it can no longer see the computer. And so now if it's trying to predict what will happen if I turn that way, obviously this depends on remembering the past. And if it can only move 3 degrees at a time and it moves 3 degrees left 7 times, then it's got to remember 7 times into the past if it's going to be able to predict eventually that, oh, there's a computer here. So that's a kind of prototypical example where it's not a Markov process. And what can we do? So one interesting idea that people have played around with is to change the structure of the neural network. Let's train a network to predict what things are going to look like at time t plus 1, given the input at time t, which might be what I currently perceive plus the action I'm about to do. So that could be the input, what I perceive right now in my camera, and the action I'm about to do. And then the output could be some encoding of what will I see next. Like, will the computer be there or not? So if we train the network as a standard feed-forward network, of course we'll have implicitly been making the assumption that this is a Markov system. We're predicting the value at t plus 1 conditioned only on values at t. But if instead we use this slightly different network architecture, we can essentially represent the past. So here's how this thing works. At time t, we input, again, the same inputs we were going to input before. But in addition, we take the value of this unit at time t minus 1. And we just copy it back and make that the input at time t. Okay, so this will be our way of capturing history, because obviously unit b at time t minus 1 is some function of the stuff that we saw at time t minus 2, or sorry, at t minus 1. B is some summary of the data at t minus 1, and then we copy it over on at t and call it input. Okay, so did I say that clearly? All we're going to do is, at every time, we're giving a new input to make our prediction, but at time t, we copy the value we used to have at t minus 1 of b, and we make that input c of t. Okay, so we're just kind of remembering what b was. Now, what makes this interesting is that we haven't specified what function of the inputs b is. That's up to the network to learn. And b is itself not just a function of these x's, but it's also a function of c. Okay, so when I copy that b at t minus 1, it's a function not only of the immediate camera input, x at t minus 1, but also of whatever history we were using, history summary we were using from the previous time. So by making this loop, b could in fact be a summary of arbitrarily long paths into the history of inputs the network has seen. So I think this is an interesting idea. It gets, again, it's kind of a mind-expanding idea. It gets you thinking about, how can I use this mechanism for learning representations and engineer it so that it ends up having to learn an appropriate summary of the history of inputs. And again, when we train this network, if we train it in the usual backpropagation way, we're training it to minimize the sum of squared errors on the output. So we're training it to make good predictions of t plus 1. And so just like those 3 hidden units in the face network had to learn the best re-representation of the input that they could learn in order to classify the face, this network has to learn the best summary of arbitrary paths back in history in order to optimize its prediction of the future, t plus 1. So it's a very nice idea in principle. I've tried this on exactly, actually, robot data doing this thing that we were just going through. And I did get it to learn a couple steps back to remember that there was actually a cup, not a computer, off on the side. But in practice, I had difficulty training it to learn very sophisticated representations of history. But it's still an interesting idea, and it's one that I haven't seen, and I haven't read every paper that's been published, but I haven't seen this resurrected in recent models of more probabilistic models of time series data. So maybe there's an opportunity here for a marriage of this interesting idea and more recent probabilistic time series models. So the one detail of this I left out is, how would you train such a network? Yes, question?
Could you also have a recurrent network where the B is fed back to multiple inputs?
Yes, so the question is, could we have B fed back to multiple inputs? Yes, in fact, we could make as many of these B's as we like and feed them all back like this. Is that what you're asking? Right. So you can imagine a whole family of graph topologies that one might design. And if I wanted a more sophisticated representation, I might want more than one unit to summarize history. Okay, so one detail I left out is, how would you train such a network? Remember when we talked about neural networks, we said backpropagation works fine on any directed acyclic graph. But we just put a cycle. But if you think about it, the cycle we put in is not a troublesome cycle because it goes over time. And so one way to think about training this is to just think of unfolding the network in time. So one way I have this network up in the corner there that has a cycle, but if I want, I can think of that. Let's suppose I have input at time t, t-1, and t-2. Well, I could make a directed acyclic graph that looks like this, that covers that window of time. And then I could train that using backpropagation, no problem. And furthermore, if I want to, in the end, fold this up into a network that looks like that, then really the only thing I have to do is parameter sharing across, for example, all of the parameters here. Well, actually all of them. I want all of the parameters, like the weight here, will be identical to the weight here and here. The weight here will be identical to the weight here and here. And so when I take my gradient descent step and I update the weights here and the two corresponding places there, after I take that gradient descent step, which might now make those 3 different weights, I just take their mean and replace each of them by the mean. And that will move me down in the gradient that I really care about. And furthermore, if you think about just a recursive way of implementing this, you realize that you don't have to commit ahead of time to how deep you're going. You can simply take the entire time series that you have and set up a simple recursive strategy for training this with the shared weights so that it can cover as deep a history as you have available in your training data. Okay, so that's the idea. And again, the whole point of this example and the previous one was to get us to think a little bit more about, and a little bit more imaginatively, about the variety of kinds of representation learning tasks that we might be interested in. And, you know, by the way, I think I've said this before, but I'll say it again. When I look at the field of machine learning, I see a tremendous amount of very good research on the question of, given some representation, how do we learn a good approximation to the function for which we have training data? And I see very much less work on the question of how do we learn not functions with a fixed representation, but how do we learn good representations? I see much less work on that. And so I think that's one of the areas that I would predict over the next 5 or 10 years. We might see a lot more interesting developments on that problem just because it's not as fully explored as the one of how do we learn functions. So if you're thinking about doing research in machine learning, you might think about this as an area. Okay, that's all I'm going to say about neural networks until next lecture. So to summarize then, I think here are the high points. Neural networks are interesting because they're a way to represent nonlinear functions. You can think of them as a nonlinear regression approach. Furthermore, they can represent functions where the output variable y doesn't have to be just a single random variable. Could be a whole vector. That vector, for example, could represent the image, the robot, predict an image the robot's going to see if it does some action. The hidden layer representations give us a way of getting at this issue of learning representations that are optimal for the eventual prediction task of the network. And there's a community of people who use these to study human cognition. The downside of neural networks is that they're not that easy to train because the more complex you make the neural network, the more non-convex that error surface is that you're applying gradient descent to. And therefore, the harder it is to find the global minimum sum of squared errors point, because all gradient descent is guaranteeing is that you'll find some local optimum. And mostly for this last reason, there's much less work on these kind of neural networks in 2011 than there was in 2000. And in some ways, the field has moved towards saying, we really want convex optimization problems as learning tasks, not these non-convex optimization problems. Because even though neural networks can represent a lot of great stuff, and you might get them to learn the right weights, we'd rather have a will than a might in that statement. And so there's a kind of a shift of the field toward looking for replacements of this, where the learning problem is a convex optimization problem, where you can guarantee that you get the global optimum. Nevertheless, there's this tension between wanting to be able to find the global optimum, and therefore needing perhaps a convex optimization problem, versus having a framework that can represent a sufficiently rich set of functions that you can do what you want to do. So there's this tension there. But nevertheless, now when we think about this question of learning representations, the next thing I want to talk about is methods for learning representations that do have the property that we can guarantee. We can set up an objective function for what we want that representation to be, and then solve it optimally. And the first one of these is principal components analysis. So this is, I think of principal components analysis as another way of learning lower dimensional representations of inputs. The idea is that we're given data points in some d-dimensional space. For example, the photograph that was the input to the neural network would be a point. Each photograph would be a point in a 960-dimensional space of images, right, where each pixel corresponds to some dimension in Euclidean space, and each photograph is therefore a point somewhere in that 960-dimensional space. So generically, we assume we're given data points in d-dimensional space. We want to project them into some lower dimensional space. For example, we might want the best two-dimensional planar approximation to points that exist in three-dimensional space or higher. And with principal components analysis, we end up having a guarantee that if we use this approach, we have a re-encoding of our input that minimizes the sum of squared error when we go to reconstruct the output, when we go to reconstruct it. So here's my one-slide summary of PCA. I think of PCA this way. I'm a little unusual because of that, but that's okay. There are several ways to think of it. This is just a copy of the auto-encoding neural network we talked about last time. Remember, we talked about, oh, what if we make this the identity function? We input some set of 8 ones and zeros where all of them are 0 except for one of them. And then we try to get the network to train itself to produce the identity function, to produce at the output the same thing that we gave it at the input. But we gave it this bottleneck of only 3 hidden units that it could use. We talked about it. Somebody suggested, well, if it was good, it should learn a Boolean encoding of the 8 possible positions where the 1 could be. When we saw how it trained, indeed, that's what it did. Okay. But it was a neural network, and so what was the functional form of, what was the function that these hidden units had to follow when they computed their values based on the inputs? They were logistic functions, right? That's what neural network is. Every threshold unit is a logistic function of its input. So in PCA, we have the same kind of task. We want to come up with a lower dimensional representation of the input that allows us to minimize the sum of squared errors if we then go from the low dimensional representation and try to reconstruct that input. And just like when we train the neural network, we want to minimize the sum of squared errors. But with PCAs, there are a couple differences. One is we have a linear function instead of a logistic function for calculating these, the values along each dimension from the inputs. It's a linear function. And that makes this network less expressive than the logistic functions. But in return, what we get is no local minimum problems. So that's the trade-off. By going down to linear instead of logistic functions, we can guarantee that we can solve this. And in particular, PCA gives us dimensions here that are orthogonal. I'll say more about that in a sec. And where the top k dimensions, if we train this network with, let's say, if we use PCA to train essentially a linear network like this, if we give it 8 inputs, 8 hidden units, if we allow it to map the 8 input dimensions to 8 hidden dimensions, then obviously it can represent any linear function of, that we have in mind. And if we do that, then it has the interesting property that if we take just the top, and I'll say precisely what I mean by top in a sec, if we train it on, let's say, with 8 hidden units so that we can represent all of the linear functions, and then take just the top 3 of those 8 dimensions, then we'll end up having the 3-dimensional representation that meant that the best one you can get. So put another way, the top k dimensions in the k-dimensional hidden layer for a PCA have the nice property that they give us the linear re-representation of the input that minimizes the reconstruction error, which is not a property that we had when we trained our neural networks, right? When we train it, we get those 3 hidden units. We don't know what's going to happen if we take out one of those units. We don't know if the other 2 will be the best 2 you could get or not. But with PCA, they are. Okay, so let's look at an example. Here's an example of applying PCA to reconstructing faces. Okay, so here's a set of faces that we'll train our PCA system on. And again, now PCA is going to learn a lower dimensional representation of these input faces, where each feature is a linear function of the input face. Here's a set of faces. And then given that lower dimensional representation of the faces, there will be a linear function that reconstructs the faces from that lower dimensional representation. What I'm showing you here is that linear function. So in other words, if we have, I can't tell you what the resolution of these faces is. It's high. It's probably more like 100 by 100. So it might be 10,000 dimensional input. This shows us the weight matrices here for a 1, 2, 3, 4, 5 by 5, 25 dimensional lower dimension representation. So it's like this network has 25 hidden components discovered by PCA as a linear function of the inputs. And these are the weight matrices for each of these. In other words, the output face that's being constructed is this image multiplied by whatever value this first dimension has when you encode the face, plus this weight matrix multiplied by whatever value this hidden unit has, etc. In other words, the reconstructed face is just the sum over those k dimensional components in k-dimensional space. So it's a weighted combination of these different weight matrices, which people like to call eigenfaces for possibly obvious reasons. But essentially what PCA is doing here is it's saying, even though these are probably like 100 by 100 images, which would mean there are 10,000 dimensional images, we can get a pretty good reconstruction, and I'll show you on the next slide how good, of any of those images if we just represent it only in terms of 25 components and use these 25 weight matrices to then explode the 25 numbers back into the image by taking a weighted linear combination of these eigenfaces. So that's kind of interesting, and it's similar to what we saw with neural networks, but again, different because these are linear functions. Yes?
These are not necessarily the dimension of the dimension, the k dimension, right? These are the top k detections.
These are the top k.
In some d dimension, which is the resolution of this small image.
So in PCA, what we do is we actually, if this is 10,000 dimension, the straightforward way to use PCA is we learn a 10,000 dimensional re-representation of this 10,000 dimensional input. And then we have a way of sorting those 10,000 dimensions. And if we take the top k of them, in this case the top 25, then we're guaranteed to have the best reconstruction you can get out of an orthogonal basis that you can get that has 25 components. So that's actually what I did. Okay, so here are the reconstructions of the faces, just to show. So this top panel shows what happens if we use just one of the, essentially if we represent the face as just one-dimensional, we map all the faces down to a one-dimensional space. And so all we have to represent the difference between your face and mine is a single real number. And then the question is, what eigenimage should we multiply that real number by? What is the representation of these, the best representation of faces if I only give you a single real value for encoding them? It's here behind some pop-up menu. Here it is if we use 2. Then here's the reconstruction of the face using 2 and adding one additional component at each step here. So here you see it's, what's that, 25. So here's the 25-dimensional reconstruction of the face from 25 numbers, 25-dimensional representation. And here it is if we add 8 at a time. So that would mean we're up to 80 plus 24. So this is 104, this one. And you can see it's visibly better than it was if we just used 25. But the interesting thing is that 25 is really not bad. You can tell who it is from 25. So this is kind of interesting, right? What it's saying is, weirdly, you and I, our faces can be distinguished or encoded well enough to distinguish who we are if we represented each of our faces by just 25 real valued numbers. And then how do we encode those numbers? And how do we decode those numbers to get from our face to those and from those? Well, it's just a linear function. Right? A weighted linear combination of those eigenfaces that we looked at. So in some sense, those face-like weight matrices that we looked at here are really the basis set even though faces are really, if this is a 10,000 dimensional photograph, they're really points in some 10,000 dimensional Euclidean space that I don't know how to describe. But essentially what this is saying is we could make that as small as 25 dimensions. And now each face is just a point in 25 dimensions. And with the right encoding, and PCA helps us learn that, we can represent much of the variation across different faces.
Is it important to separate out your classes really cleanly before you try to do PCA? So you get all your hands over in one bucket and all your faces in another bucket?
Oh, I see. Yeah, the question is it important to, if you had hands in faces, would you want to put those into different buckets and do PCA separately on them? Yes, you would. And in fact, there's interesting work, which we're not going to cover in this class. Maybe we should. Wow, maybe I'll put it into next lecture. There's interesting work where people said, well, what if we don't bucket it? What if, in fact, we had images collected from arbitrary photographs outdoors or indoors? Could we set up a system where we learn useful lower dimensional encodings of arbitrary images? And so that would have, unlike these images, which are, every face is about the same size and it's centered in the photograph and everybody's looking kind of the same direction. So there's a lot of standardization here. But people have looked at the question of, can you learn codings for arbitrary images? And the answer is surprisingly well, but it's not using PCA. So simple linear functions like this don't really do it. Maybe we'll talk about that. Just one more sentence on that. One of the people who did some of the nicest work on this, actually two people, Terry Sanowski in San Diego and Mike Lewicki, who used to be at CMU but recently moved to Cleveland. They took a bunch of images, natural scenes, trained a lower dimensional encoding, which was not PCA, but something else. And then they compared it to what people know about the encoding in visual cortex of images. That's why they did it. They were trying to see if they could build a computational model that predicted neural responses in visual cortex. And they figure visual cortex must be confronted with that problem. So let's try to train a system that can handle arbitrary images. And they had some very nice results showing, and maybe at least I'll try to bring in a picture of what their codes look like. They're very different from these eigenfaces. But the codes that they found actually ended up matching a lot of the characteristics of particular regions in visual cortex that appear to be coding images in some kind of similar way. Okay, so there's eigenfaces. And why do we call these things eigenfaces to begin with? By the way, I just thought it would be fun, having looked at those eigenfaces, to go back and look at this picture again. And you can see those things really don't look like the eigenfaces. It's a different kind of thing going on. One reason they don't, of course, is that here we're using logistic functions instead of linear. But another reason is that PCA only deals with the question of an autoencoding. That is, PCA only deals with the question, how do I find a lower dimensional representation that minimizes the reconstruction error of the input? Minimize the error in reconstructing those input faces. And here, of course, we have a different task. We're not trying to output the input image. We're trying to output a decision about what direction the face is looking for. So in this sense, PCA is what I would call, what many people call, an unsupervised approach to learning lower dimensional representations. Unsupervised in the sense that there's not a classification task, and so we just default to minimizing the reconstruction error. In contrast, these kind of neural networks It's really a supervised dimensionality reduction problem, because we're trying to minimize some other kind of prediction error, whatever function we're training on. So broadly speaking, when I look at the landscape of approaches to learning representations, one of the major distinctions I see is there are approaches like this one that I would consider supervised. They're learning representations for some particular purpose, prediction problem, versus PCA, which is trying to come up with an efficient code of the input. It's unsupervised. Okay, so PCA, let's look at the details of this now. So here's the way to think about it. Suppose we have this data set, d-dimensional vectors. Those could be our images, for example. And of course, we can represent each image as just a vector with 30 times 32 features in it. And the nth one of those, I'll use the superscript as we have been doing before. So we haven't done much linear algebra in this course. I'm going to use some vector notation and linear algebra notation here. It can't be helped. But we can think of it this way. So here we have, for example, a bunch of points in a two-dimensional space, x1 and x2 being our dimensions. And we can represent any d-dimensional thing as the sum of a weighted linear combination of d orthogonal vectors. In other words, if I have, let's think about 3 dimensions here, and suppose my 3 dimensions are represented by this edge of the table, and a vertical thing coming straight up out of the table. And so now you have an x, y, z coordinate in that coordinate frame. Well, whatever your x, y, z coordinate is in that coordinate frame, those would be your values, x1, x2, x3. Now, I could think about this coordinate frame instead. Let's use this one. I didn't have a ski injury on that thumb, so these are more orthogonal. I could think about this coordinate frame instead, where the origin is here. You have a different representation, a different coordinate in this frame than you do in that one. The origin's at a different place. These things are not aligned in the same directions as those. But in a sense, it doesn't matter which of these two I use, right? They span the same 3-dimensional space. That is, any point that can be represented in this 3-dimensional coordinate frame can also be represented in this 3-dimensional coordinate frame. Therefore, they span the same space. In fact, any 3-dimensional orthogonal, meaning mutually perpendicular, orthogonal basis set of coordinates will suffice. And so think about it that way. And dimensionality reduction is all about going from the original coordinate frame, those 30 times 32 dimensions in the original Euclidean space, to some other coordinate frame in which we're going to represent those points. And if I go from a 3-dimensional one to a different 3-dimensional one, well, of course, there'll be no loss. I can still represent any face. But if I want to go from a 3 to a 2-dimensional coordinate frame, well, then I'm going to have some loss. And the question is, how can I minimize that loss? And that's what PCA does. So we can represent any of these vectors starting out in one coordinate frame, like the x1, x2 frame. We can represent it instead in terms of the coordinate frame represented by u1 and u2, for example, here on this plot. And that just means the vector x, any one of those points, is a vector from the origin up to the point. Any of those vectors can also be represented as the sum of the projection of that point onto u1 plus the projection onto u2 with weights z, z1 and z2. Okay. And so what PCA does is solves the following problem. suppose we want to go from d dimensions to some much smaller m dimension space. And so then what I want to do is I want to find the orthogonal basis, the set of u1 through u2 through um, the orthogonal basis, that minimizes my reconstruction error, which is just the difference between what I would reconstruct and the original. And furthermore, well, and the way that it's going to do it is it's going to construct its prediction of x by a basis set where the origin is centered at the mean, and then where it just projects the point onto the different vectors. And so, for example, given this set of red dots in this plot, the mean is right, oh, that's right here. That's the mean of those points. And so what we're going to do is we're going to represent any of those, we could represent any of those red points as, let's take this one. We could project it onto u1 and say that's its u1 coordinate. We could project it onto u2, that's its u2 coordinate. And then by summing that plus that, we get back this. And so what PCA does is essentially it learns what are u1 and u2. And it learns them so that in an order. The first one, u1, has the property that if you can only use one dimension, it's the best one. It's the dimension, it's the direction that minimizes the sum of squared errors if you can only use one component. And then u2, the next one it learns, has the property that given that you've already learned u1, and that doesn't perfectly allow you to reconstruct all the points. For example, suppose we learn u1, then all these points are going to be mapped. This point will be mapped here. This point will be mapped here. It'll be had a negative coefficient on u1. This one will be mapped here. This one will be mapped here. But there will still be these errors, those lines. If we go to reconstruct it from just the u1 coordinate, all the reconstructed points will lie along u1. And so then u2 has the property that given that we're already using u1, u2 is a vector that must be orthogonal, perpendicular to u1, and be in the direction among those that are perpendicular, in the direction that minimizes the sum of squared errors if you use the 2. So that's what it does. I want to go through the details of this. I'm going to go through them kind of quickly, and I urge you to read the Bishop reading and tutorial article that I'll put up too. But this is very nice and very foundational stuff. If you understand this, it's kind of the basis for a lot of work on linear dimensionality reduction methods. So let's go through it. So as we just noted, so again, this is what PCA is doing. It's just finding a basis. In this case, if we just have this two-dimensional data up in the corner, and we allow it to learn a two-dimensional basis, it will learn this u1 and u2. Because u1 has the property that if you only get one dimension, that's the best one in terms of minimizing the reconstruction error. And then u2 has the property that it's the only other orthogonal vector, and therefore it's the best one. But you get the idea. Okay, so now if we ask what is that reconstruction error, the interesting thing is, of course, if we allow it to use m dimensions to reconstruct, to encode the input, and d is the dimension that x is actually in, then if m equals d, then we get 0 reconstruction error, right? U1 and U2 do a perfectly good job of representing the x's. We could map back to the original x1, x2 coordinate frame if we cared, with no loss of information. But when we do get error, it can only happen because we use m smaller than d. So these might be points in 3 dimensions, and I only get to use a plane. So I've got to pick the best plane. And maybe those points are in some kind of blob like this. Then I'd like the plane to be aligned kind of along the direction that the blob spreads out informally. So the only way I can get error is when I have missing components. And so the expression I can write for the error is just the sum over those missing components. I'm only getting to use m, but out of the d dimensions, let's sum over those missing components, m plus 1 up to d, of how much squared error I get along that dimension I. So in other words, if I had points in 3 space, and I'm mapping in them to this 2-dimensional plane, but some of them aren't actually in that plane. I've picked the best plane that kind of minimizes the sum of squared errors, but some of them just lie outside the plane anyway. Well, if I had a third u sub 3, I'd capture it. And the error that I have is actually the distance from that point to the plane, which is the projection of that point onto u3 from the plane. And that's what this thing is saying. It's just the sum over those missing dimensions that I left out of how far they are from the plane that I'm using, from the dimensions, the lower dimensional space I'm using. So now it gets interesting. I can show that this is equal to this expression, where sigma is the covariance matrix. Now, what is covariance? Let's go down and look at. So sigma is covariance matrix, and I define covariance between 2 vectors as a matrix where the ijth element is the covariance between x sub I and x sub j. For example, x1 and x2 up in this plot in the corner. The covariance is simply the sum over all those red points, or our estimate of the covariance is just the sum over all those points of the difference between the point and the mean for dimension x sub I. So for example, the mean for dimension x1 I would say is about here. The mean for dimension x2 is about here. And so that's x bar sub 1 and x bar sub 2. And the covariance is just the product of how far x1 varies from its mean times how far x2 varies from its mean for every one of those points, summed over every one of those points. So if they co-vary in the same direction, then I'll get a big positive product here. If they vary kind of randomly, independently of each other, then I'll get a covariance with terms close to 0. So it captures how interdependent these things are. And so we can represent it this way. And then it turns out this expression is minimized when those dimensions we're trying to solve for, the u sub I, are the eigenvectors of this covariance matrix. An eigenvector simply means that if we multiply the vector by that matrix, we get another copy of that same vector multiplied by a scalar, lambda I, which is the eigenvalue, called the eigenvalue of ui for sigma. Okay, so if you've had your course in linear algebra, this is all coming back to you, and you know this. But this basically turns this into a nice linear algebra problem where basically all we have to do is find the eigenvalues of the covariance matrix. So in fact, here is the algorithm. If we have a set of data, like those red points up in the corner, first we build a matrix X which has the n points. And in each of them in their original d dimensions. And each row in that matrix corresponds to one of these points. Then we make that have a zero mean. Essentially, we subtract out from each of the vectors in that matrix the mean of the vectors. So we essentially find this point, which is the mean of all the points, and we subtract that out. So now we have a zero-centered set of points in X. If we average over all the rows of X, the mean is now 0. Now we find the covariance of that. And then we find the eigenvectors and the eigenvalues. Those are the u sub I and their corresponding lambda sub i's. And then the principal components are just the m eigenvectors with the largest eigenvalues. Okay, so when we do this here, for example, this turns out to be the first eigenvector, meaning when we do that, this is the first eigenvector. When we multiply that by a covariance matrix, we get itself back with some scalar multiple of itself back. And it has the largest scalar multiple of all the eigenvectors. Therefore, it's the first one. And the fact that it has the largest eigenvalue is an indicator that it points in the direction of maximum variance of the data. That's what it means, actually, in this case, for it to have the largest eigenvalue. And as you can see, indeed, it does. It points in exactly the direction you would point if I asked you, what direction does this cluster of data what is the direction of maximum variance of the data? And so that's the first eigenvector. And then the second one is orthogonal to the first one and maximizes the variance, or points in the direction of maximum variance conditioned on the eigenvectors you've chosen already and the fact that this must be orthogonal to those. Okay, so then if we use those to, for example, we might say, okay, we want a one-dimensional reconstruction of this two-dimensional data. Well, for one-dimensional, we want to use this first eigenvector. We'll say, let's just use that one hidden unit. That'll be our one dimension for encoding these points. And then we get these red points if we try to reconstruct them from just that one-dimensional data. And of course, all those red points that we construct, they'll lie right along that dimension because the only way we can reconstruct them is to multiply their coefficient by that vector. But as you see, there's still a residual error. Those points aren't exactly where the blue original ones were. But if we now allow using the second dimension, of course, we'll be able to then add in another orthogonal vector to their original reconstruction from the first dimension and get back the full blue points. All right? Okay, so the algorithm is straightforward, and if you have a small set of data, you can actually sit down in MATLAB and just type this into MATLAB and do it. And MATLAB has this nice function for calculating eigenvectors of a matrix, so you don't even have to do that yourself. And this really works, and in fact, that's how I made these little plots here. These are, so it's very easy to implement in MATLAB, as long as the dimension is not too big. And so the real problem is if you have larger dimensional stuff like images with maybe 100 by 100 pixels, that's 10 to the 4th pixels. And so the problem is that covariance matrix, which has to measure how much each of those pixels covary with each of the others, that's got 10 to the, if we've got 10 to the 4th pixels, we have that number times 2 terms in the, or squared, I should say, squared, in the covariance matrix. So that gets to be problematic. And MATLAB will not like it at all if you ask it to to do very large things. And so there's a technique called singular value decomposition, which is really your friend if you ever want to do linear dimensionality reduction problems. And singular value decomposition also is available in MATLAB. It's different from the eigenvector calculating thing, but it's a very nice thing, and it scales very well. And here is the idea. And I took this from a very nice overview on PCA that was written for computational biologists by a guy named Wall. But here's the idea. SVD is called for singular value decomposition. Essentially says we can solve for the eigenvectors by decomposing our data X. So X is our data. We have one row per data point in X. So if I have m data points here, and each of them is of n dimensions, then I just assemble this data matrix X, and I zero center it. And then I can express that matrix as the product of three other matrices. The easiest one to think about is S, because S is a diagonal matrix. It has zeros off the diagonal everywhere. And those, it's an n by n. Remember, n was the original dimension of the data. And each of the values in S is an eigenvalue for one of the eigenvectors. V transpose is another matrix where the rows of that are the eigenvectors of X transpose X, which is the covariance. And so if we've zero-centered X, that is subtracted out the mean so that the average of all the points in X is 0, then X transpose X will be just some constant times the covariance matrix of X. And the eigenvectors here will be the principal components. So essentially, SVD gives you the principal components in V transpose. And it gives you each of their eigenvalues in S. And most implementations of SVD actually go to the extra step of sorting the rows of V transpose in S so that the eigenvector values go from largest to smallest. So that if you want the top K, all you have to do is, or the top R, for example, you would just chop out a subset of that matrix and the subset correspondingly over here. And then U times S actually gives us the coordinates of each of the points in that eigenspace, in the space, in the space defined by these eigenvectors. Okay, so SVD is just a nice thing. You can find papers that tell you the details of how to implement it. But the good thing is very few people do, because they're very good packages for doing singular value decomposition that are easily available, including in MATLAB. And this thing scales up to very high dimensions. So you can do things like images without any problem with SVD. Oh, okay. So, so again, here's the algorithm written down in one spot. So if you want to use SVD to find the principal components, you create your X matrix, you subtract out the mean, giving you this matrix X with one row vector per zero-centered data point. You solve the SVD, and then you just read out the eigenvectors from V and S. So it's a nice practical way. So if you're in your project, if you're looking for something interesting to do in terms of projecting things into low dimension, this is eminently doable and something you could easily do in the context of one of your projects. Okay, and so then if we, then you might ask, well, when we're all done, right, so now we have this matrix X, and we say, well, that's U times this diagonal times V transpose. But now what if, okay, so maybe I've learned this lower dimensional representation, but what if I actually want to now take a photograph, an image, and project it into that lower dimensional space? What do I do? Well, it's very straightforward. If X is your data, say a new image, a new face, then you just multiply the vector X times V transpose, that matrix which has all the rows are the eigenvectors, are the principal components. And so if you just multiply the column vector X times that, you'll be projecting that onto each of the dimensions that are in that lower dimensional space. So it's just a simple vector times V transpose product. Okay, so there's SVD. And it's really a widely used thing. It's one of the first things many people do with their data when they get data, just to see if it's high dimensional data. It's often a very good idea to first just project it into some lower dimensional space. And you can use this for many purposes. For example, one thing people often do is project their data into the lower dimensional space just to see, if we're starting out with 10,000 dimensions, and it turns out we can reconstruct things almost perfectly with just 20 dimensions, then that tells you something about the real complexity of your data. Maybe 10,000 pixels, but if they're all faces of me, there's not that much variance if I'm smiling or frowning. So it'd probably be a fairly small dimensional space that all that high dimensional photograph data projects down into. One reason people use PCA is to find outliers. Remember those red points in the cloud we were looking at? Well, if I put one way over here, then when I did my lower dimensional representation of those red points, that one way over there would be much more difficult to reconstruct. The reconstruction error of it would be much smaller because the lower dimensional PCA components that I'm using are designed to capture, well, they're minimizing the sum of squared errors over all the things. So they're going to capture what's good for most of the data points, and the outliers will be easy to identify just as high error things. So that's another reason people do it.
How does this compare to what you saw in the beginning of the class where you had a lot of pictures and you were just using the neutral?
How does this compare to the case where we had a lot of features? I didn't hear the end.
And we were just using the neutral information gain.
Oh, where we're using information gain. So how does this compare with using information gain to choose features? Is that the question? So the difference here is really, this is related to the earlier question about how does this relate to feature selection. And so when we used information gain to select features, we're choosing a subset of the features. And what we're doing here is we're really synthesizing a new feature, which is a linear function of all of the original features. So if I understood your question correctly, it was really about the difference between doing feature selection versus projecting the points down to a lower dimensional space. In the lower dimensional space, if you think about the features, the use of eyes in this lower dimensional space, they're not a subset of the original features. They're just different features.
Yes, I mean, which one is more appropriate?
Which one is more appropriate?
In which case?
Yeah, that is a good question. Which one is more appropriate? So I would say I always feel less nervous if I project things into lower dimensional spaces than if I throw away features. The reason is I'm afraid of throwing away useful information. And so if I have 10,000 features, again, think about those face images. If I picked 25 of the 10,000 pixels, I bet I'd have a pretty bad summary of the information that was in the photograph. On the other hand, if I use 25 PCA components, I've got 25 linear functions of all 10,000 features. And so I feel much more comfortable doing that because now I know I've thrown away some information, but I've thrown away, in a sense, the least information that I possibly could, given that I'm synthesizing features which are linear functions of everything I started with. So the one reason why I might go the other way is if I have a data set where I have a lot of features, and for some reason, I'm pretty sure ahead of time that only 5% of those features matter. It's just that I don't know which 5. If I'm in that situation, then I'll probably do feature selection instead, because all those other features are just noise, and they're just going to confuse the issue. So it really boils down to whether I have some initial assumptions about whether all the features have a little information, then I want to do this dimensionality reduction. Or most of the features have no information, only a small subset, but I don't know which ones are relevant. In that case, I'll do feature selection. And it's the same answer to, I would give almost identical answer if instead you had asked the question, when would you use a decision tree learner versus logistic regression? And for the same reason, I would give almost the same answer. I'd say, well, if I'm going to succeed with decision tree learning, it's because only a small subset of the features are going to be chosen by the tree. And the tree will just ignore all those other features that it didn't need. They didn't have high mutual information anyway. Whereas if I think all the features have a little bit of information, then I'll use something like logistic regression, because that gives my learner the opportunity to have some weighted combination of every feature. And so it's a very similar question. Okay, let's stop there for today, and we'll pick this up and talk about some more methods next time.